Hello students, I welcome you all for the online lecture series of Design of Steel Structure. In today's lecture, we will be studying numerical on design of column. The following is the statement of the numerical. Check the adequacy of ISHB 450 about 85.4 kg per meter to carry a factored compressive load of 750 kilonewton at a eccentricity of 270 mm about the major axis. The effective length of the column is 3 meter. Consider only the section strength. This is the diagram of our column. Following is the given data. PU, that is ultimate load, is equals to 750 kilonewton. As the load is factor load, there is no need to multiply the given load by the factor of safety, that is 1.5. Then eccentricity is about the major axis, hence it is EY, which is equals to 270 mm, and L effective, that is equals to KL, which is equals to 300 mm. Therefore, ISHB 450 about 85.4 kg per meter is utilized to design the section. We have to find the section strength, that is nothing but N upon Nd plus Mz upon Mdz, and this value should be less than 1. Then the eccentricity is of 270 mm in the y direction, and the moment due to this eccentricity is 270 into 750 into 10 raised to 3 Newton. Thereafter, we need to write down the properties of the section. The solution, the first part is we have to write down the properties of the section. From the steel table, we got the value of H as 450, A, that is area of the section, as 11114 mm square, 11,114 mm square. BF is 250 mm, TF, which is equals to thickness of the flange 13.7 mm, TW, thickness of the web 9.2 meter mm, RZ 187.8 mm, RY 51.8 mm, H1 386.2 mm, ZPZ is equals to 1955.03 into 10 raised to 3 mm cube. Then classify the cross section. First one is the flange criteria, BF upon TF. As it is I section, we need to divide the BF by 2 and divide it by the TF again. Substituting the values of BF and TF, the value is 9.12 and it is less than 9.4 epsilon, hence our flange is plastic. Then H1 upon TW, which is equals to 386.2 divided by TW 9.8, and the value is 39.40 and it is less than 84 epsilon, hence our web is also plastic. As our flange is plastic, web is plastic, section is also plastic, and therefore the value of beta B is equals to 1. Then our PU is 750 kilonewton and moment is equals to 750 into 0.27 is equals to 202.5 kilonewton meter. The third step is to calculate the design strength of the section. Nd is equals to Ag into Fy divided by gamma m0. Substituting all the values in the mm, we will be getting the value of Nd as 2525.90 kilonewton. Then mdz is equals to beta b zpz into fbd. For fbd, we have to calculate KL upon RZ, which is equals to 15.97 approx equals to 16 mm. H upon TF is equals to 28.18. Then from table number 14, page number 57 and table number 13A for FBD, TF, that is KL upon RZ, these values are shown, and by using the interpolation we get the value as 3166.54. Then again we are interpolating the value for 3166.54 from table number 38. FCRB is equals to 3166.54, Fy is equals to 250. By interpolation we get the value as 227.3 mm. So mdz is equals to, substituting the value of fbd into the formula, mdz is equals to beta b is 1, zpz is 1955.3 into 10 raised to 6, and fbd is equals to 227.3. We get the value of mdz is equals to 444.378 kilonewton meter. Then substituting these values into the formula, n upon nd plus mz upon dz, and this should be less than 1. The value is 0.75, which is less than 1. Hence our section is safe to transfer the given eccentric load. Then the plastic hinges. What is a plastic hinge? A plastic hinge is a zone of yielding due to the fracture in the structural member. A strain hardening action usually occurring at the location of the maximum bending moment, and hinges are formed causing the large deformation and rotation by slightly increase in the load. Then a structure can support the computed ultimate load due to the deformation of the plastic hinges. The member remains elastic until the moment reaches a value of mp. Any additional increase in the moment will cause the beam to rotate it with little increase in the stresses. So this is the diagram of an I section and area of the yielding subjected to the load W. The depth of the section is D and width of the section is B. The plastic moment of a section. The maximum moment of resistance of a section which is fully yielded, Mr is equals to I by Y into sigma. I by Y is nothing but the Z, and therefore the Z, that is the section modulus, which is geometrical property of a cross section used for the design. ZE is elastic section modulus, and this is applied up to the yield point of the material, and ZP is equals to plastic section modulus, which is equals to elastic yielding and is assumed, and plastic behavior is assumed to be an acceptable limit for the design. The diagram gives the same idea. Consider a yield cross section of a beam having bending stress distribution rectangular. For simply supported condition, the top fiber will be in compression while below neutral axis, the bottom fiber will be in the tension. The compression will be is equals to Fy into A1 and tension will be equals to Fy into A2. For equilibrium, the force in the compression must be equals to tension. So compression is equals to tension. Fy into A1 is equals to Fy into A2. From the figure, A1 is equals to A2 is equals to A by 2, as neutral axis have equal area axis is equals to equal area axis. Therefore, MP is equals to Fy into A by 2 into Y1 bar plus Fy into A by 2 into Y2 bar. Hence, MP is equals to Fy into A by 2 into Y1 bar plus Y2 bar, and MP is equals to Fy into Zp. Therefore, Zpz is equals to A by 2 into Y1 plus Y2, and Zpy is equals to A by 2 into X1 plus X2. So this is our expression for Zpy and Zpz. Zpy and Zpz. So this is the I section. This is A1. This is A2. The Y1, that is the distance from of A1 from the centroid axis. Y2, the distance of A2 from the centroid axis. So Y1 bar is equals to A1 Y1 plus A2 Y2 divided by A1 plus A2, and Y2 bar is equals to A3 into Y3 plus A4 into Y4 upon A3 plus A4. Similarly, for calculation of Zpy, A1 A2 in the y direction, Z1 distance from the centroidal axis, Z2 of A2, hence Z1 is equals to A1 Z1 plus A2 Z2 upon A1 plus A2 divided by, and Z2 is equals to A3 Z3 plus A4 Z4 into A3 plus A4. So the question: a corner column located in a bottom story of a brace frame is subjected to a factor load of Pu is equals to 1100 kilonewton, Mz is 135 kilonewton meter, My is 70 kilonewton meter. The effective length of a column is 3.75 meter. Design the beam column assuming the steel grade Fe410. We have to solve this numerical in the next lecture. Keep watching and subscribe the channel. Thank you.